Good day, everyone. Welcome to our new discussion about Earth science. Today, we will be discussing the rock cycle and igneous rocks. In this video, you will learn how the three main types of rocks are related and how Earth processes over geologic time change a rock from one type into another. Okay, so let's start with rock cycle. Inside the crust, rock components are slowly but constantly being changed from one form to another, and the processes involved are summarized in the rock cycle. So the rock cycle is driven by two forces. First, the Earth's internal heat engine, which moves material around in the core and the mantle and leads to slow but significant changes within the crust. And second, we have the hydrological cycle, which is the movement of water, ice, and air at the surface and is powered by the sun. The rock cycle is still active on Earth because our core is hot enough to keep the mantle moving. Our atmosphere is relatively thick, and we have liquid water. On some other planets or their satellites, such as the Moon, the rock cycle is virtually dead because the core is no longer hot enough to drive mantle convection, and there is no atmosphere or liquid water. Okay, so the rock cycle takes place both above and below the Earth's surface. The rock deepest beneath the Earth's surface and under extreme heat and pressure is what we call metamorphic rock. This metamorphic rock can be melted and become magma. So when magma cools below the Earth's surface, it becomes intrusive igneous rock. So if magma cools above the Earth's surface, it is extrusive igneous rocks and becomes part of the outcrop. Okay, so the outcrop is subject to weathering and erosion and can be moved and redeposited around the earth by forces such as water and wind. As the outcrop is eroded, it becomes sediment which can be buried, compacted, and cemented beneath the Earth's surface to become sedimentary rock. As sedimentary rock gets buried deeper and comes under increased heat and pressure, it returns to its original state as metamorphic rock. So rocks in the rock cycle do not always make a complete loop. It is possible for sedimentary rock to be uplifted back above the Earth's surface and for intrusive and extrusive igneous rocks to be reburied and become metamorphic rock. Okay, so we have three types of rock: the igneous, sedimentary, and metamorphic rock. Igneous is melting of rocks in hot, deep crust and upper mantle. So the rock forming process by crystallization, solidification of magma or lava. So for example, we have the coarse clay, crystallized granite. Next, sedimentary, weathering and erosion of rocks exposed at surface. So deposition, burial, and lithification are the primary process. So for example, the cross-laminated sandstone. Lastly, we have the metamorphic, rocks under high temperature and pressures in deep crust and upper mantle. So recrystallization in solid state of new minerals. So for example, we have gneiss. Okay, So in the discussion of the rock cycle, igneous rocks form as magma or lava cools and crystallizes. Magma is a molten rock that is most often generated by melting of rocks in Earth's mantle. Although melting of crystal rock generates some magma. Once formed, a magma a magma body buoyantly rises toward the surface because it is uh, it is less dense than the surrounding rocks. So when magma reaches the surface, it is called lava. Okay, so on solidification occurrence of igneous rocks. So when molten rocks solidifies at the surface, the resulting igneous rocks are classified as extrusive or volcanic, named after the Roman fire god Vulcan. Most magma loses its mobility before reaching Earth's surface and eventually crystallizes deep below the surface. Igneous rocks that form at depth are termed intrusive or plutonic, named after Pluto, the god of the underworld in classical mythology. So intrusive igneous rocks remain at depth unless portions of the crust are uplifted by geological process like folding. So texture classification of igneous rocks. So as magma cools, the once mobile ions begin to arrange themselves into orderly patterns, a process called crystallization. As cooling continues, numerous small crystals develop and ions are systematically added to these centers of crystal growth. So when the crystals grow large enough for their edges to meet, their growth ceases because of lack of space. The rate of cooling strongly influences crystal size. If magma cools very slowly, ions can migrate great distance. So consequently, slow cooling results in the formation of fewer, larger crystals. And on the other hand, if cooling occurs rapidly, the ions lost their motion and quickly combine. So this results in a large number of tiny crystals, all competing for the available ions. Therefore, rapid cooling results in the formation of a solid mass of small intergrown crystals. Okay, so cooling rate is the main factor that determines texture. Okay, so the faster the cooling process, the lesser the finer the igneous rocks, the slower the fewer and larger crystals will form. Okay, so a phanetic or fine grain is the fast cooling rate, and phaneritic or coarse grain is the slow cooling rate. For pyritic has phenocryst, large crystals. Vesicular has voids or vesicles. So when this happens, gases dissolved in the magma are able to come out of solution, forming gas bubbles inside it. Glassy, non-crystalline. To describe the size, shape, and arrangement of the mineral grains that make up a rock, geologists use the word texture. Texture is an important property because it allows geologists to make inferences about a rock's origin. So based on careful observation of crystal size and other characteristics. Rapid cooling produces small crystals, whereas very slow cooling produces much larger crystals. Okay, so as you might expect, the rate of cooling is slow in magma chambers that lie deep within the crust, whereas a thin layer of lava extruded upon Earth's surface may chill to form solid rock in a matter of hours. Small molten blobs ejected from a volcano during a violation eruption can solidify in mid-air. So again, a phanetic is fine grain and phaneritic is coarse grain. And when we say mafic, it is a dark colored minerals which is uh, low in silica content, and falsic is rich in light colored minerals and has a high silica content. Okay? So granite and rhyolite have the same chemical composition but different texture, as well as diorite and andesite. Gabbro and basalt have the same chemical composition but different texture. Gabbro have larger crystals than basalt. Okay. So for pyritic texture, form through two stages of crystallization were in magma, partly cooled below the surface of the earth, providing time for the large crystals to grow, to phenocryst, before it is extruded to the surface, forming the fine-grained matrix, or the ground mass. Okay, so for pyritic textured igneous rocks can form in either fine grain or coarse grain. Next, we have vesicular texture. Voids are voids created by rapid cooling, which causes air bubbles to be trapped inside. So as what can you see in the picture? Next, we have glassy texture. So if a rock looks like a block of colored glass with no visible mineral crystals, it has a glassy texture. Superficially, a glassy texture suggests cooling that was so extremely fast that no crystals could form. Okay, so composition of igneous rocks. So igneous rocks are composed mainly of silicate minerals. Chemical analysis shows that silicon and oxygen, usually expressed as the silica content of a magma, are by far the most abundant constituents of igneous rocks. As magma cools and solidifies, these elements combine to form two major groups of silicate minerals: the dark silicate and light silicate. Okay, so the dark silicates are rich in iron and or magnesium and are comparatively low in silica content. Okay, so olivine, pyroxene, amphiβol, and biotite mica are the common dark silicate minerals of Earth's crust. By contrast, the light silicates contain greater amounts of potassium, sodium, and calcium and are richer in silica than dark silicates. Light silicates include quartz, muscovite mica, and the most abundant mineral group, the feldspar. Okay, so I have examples of the igneous rocks that form from mafic, intermediate, and felsic. So in mafic, we have gabbro and basalt. In intermediate, we have diorite and andesite. And felsic, we have the granite and rhyolite. Okay, so classification of igneous rocks. So in this side, we have the texture of igneous rocks, felsic and light color, intermediate and intermediate color, mafic and dark color. And also in this side, we have the cooling history. For example, slow cooling and coarse grain, gabbro, and it is a mafic and dark color, so which means it it has a low silica content. Okay, so how to classify igneous rocks? So we can classify igneous rocks by its composition and texture. So in composition, through its silica content, and in texture, through its location, magma formation, and the cooling rate. So I have here some examples of igneous rocks. So first, we have pegmatite, a light-colored, extremely coarse-grained, intrusive igneous rock. So most pegmatites are composed of quartz, feldspar, and mica. Next, we have basalt, a vesicular or fine-grained, dark-colored, extrusive igneous rock composed mainly of plagioclase and pyroxene. Next, we have pumice, a light-colored vesicular igneous rock. It forms through very rapid solidification of melt. And lastly, we have obsidian, a dark-colored volcanic glass that forms from the very rapid cooling of molten rock material. Okay, so that sums up everything. So I hope that you have learned something new from the discussion. Okay, so see you in the next video, and God bless everyone.